Welcome back to another episode of Disc Golf Physics. This time I want to talk to you a little bit about the concept of work and energy in terms of physics and how it applies to disc golf. Actually, I'm going to let one of my students, Nathan Wise, break down the video of Nate Perkins that Nate provided for us, the same one that I looked at in episode 1. And Nathan's going to talk a little bit about how work and transfer of energy goes into the disc golf throw. So before he gets going with that, though, I want to tell you a little bit about work and energy. In terms of physics concepts, work isn't the same as our everyday concept of work. Work is when you apply a force, a push or a pull, to an object that moves it through a distance. Specifically equals force times distance times the cosine of the angle between them, which is the reason why when we pull through in our disc golf throw, we want to pull straight through. We don't want the force to be in a different direction from the displacement. We want to maximize the amount of work done, because work also equals the change in energy. We're taking potential energy in our body and converting it into kinetic energy, the energy of motion of a disc. The more kinetic energy, the more velocity, because kinetic energy equals 1/2 the mass times the velocity squared, which if we have more energy, we get more velocity, and that's what we want. We want to get the fastest exiting velocity as the disc leaves our hand. So, with no further ado, I'm going to let Nathan talk a little bit about how we can maximize the distance of our applied force. We're applying the force from our arm into the disc, so we're maximizing the distance that force is acting over in order to maximize the exit energy, the final energy, and therefore the exit velocity when the disc leaves our hand.
Nathan here, and in this part of the video, I'll be demonstrating how applying a force over a larger distance results in a larger amount of energy being transferred to the system. In this case, increasing the distance we're applying a force throughout our throwing motion will result in a higher release velocity for the disc. Let's take a look at a very basic standing shot. Here the blue dots are outlining the path of the disc, while the red dots are outlining the thrower's right hip. We can see the greatest difference between this point at about here, where the thrower has pulled back the disc to about a distance of 0.79 meters or 79 centimeters. The thrower then applies a force throughout this throwing motion, pulling the disc forward until it reaches its release point and exits with a velocity of about 20 meters per second. Now let's take a look what happens when we add a run-up to the shot. In this shot, we can clearly see the thrower initiates his run-up, cocks back the disc, pulls through and releases with a velocity of 21.6 meters per second. Adding a run-up inherently increases the distance that this force of pulling will be applied, but I would also like to take note of the distance between the thrower's front hip and the disc again. This distance is larger than that of what we saw in the standing shot of about 0.92 meters compared to 0.79 meters. And it is also this increase in distance between the disc and the front hip that allows this shot to increase its velocity. Now, what happens if we continue including a run-up but increase this distance between the disc and the front throwing hip? Once again, we can see the thrower initiates his run-up, cocks back that disc, pulls forward, and then releases. This shot had an exit velocity of about 22.7 meters per second, which is the fastest shot we've seen yet. And coincidentally, it also has the largest difference between that front hip and the disc at a 0.98 meters or 98 centimeters. This just concludes that increasing the distance that a force will be applied thus increases the amount of energy that is transferred to the system, resulting in a larger exit velocity. Let's take a look at this shot one last time. Beautiful. Physics in disc golf.
Thanks, Nathan. That was awesome, and a great demonstration of how work and energy can transfer to increasing the exit velocity of the disc and ultimately getting more distance, because if we have a faster velocity when the disc leaves our hand, it's going to go farther in the same amount of time. Obviously, there are limitations to how far a reach back can still be effective just because of how our bodies work and how the muscles attach. But if we can, within our body dynamic, maximize the amount of displacement through which our force is applied, the better our shot's going to be. Thanks for watching.